The silent, inky canvas of the cosmos stretches out, an expanse so vast it defies human intuition, punctuated by the distant, flickering testimony of billions upon billions of stars, each a potential sun for orbiting worlds. The question, ancient as philosophy itself, yet newly sharp with the edge of modern astrophysics and astrobiology, echoes across this void: is there life beyond Earth? This singular query is not merely a matter of idle curiosity, it is a profound interrogation of our own place in the universal order, a nexus where empirical science collides with existential dread, encapsulated most famously within the enigmatic framework of the Fermi paradox. To truly grapple with the possibility of extraterrestrial existence, one must first establish the raw ingredients and the necessary timeline. Our understanding begins with the Copernican principle, or the principle of mediocrity, which posits that Earth and our solar system are not unique or privileged locations in the universe. If the physical and chemical laws observed here are universal, a premise robustly supported by cosmological observations, from the cosmic microwave background radiation to the spectral analysis of distant galaxies, then the processes that led to life here should, statistically, have occurred elsewhere, perhaps countless times over. The foundational components for life as we know it, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, are cosmically abundant, forged in the fiery crucibles of supernovae and distributed across interstellar molecular clouds, the very nurseries of future stars and planetary systems. The census of exoplanets, dramatically expanded by missions like Kepler and now TESS, has transformed the landscape of this debate from theoretical speculation to statistical probability. We now know that planets are not rare appendices to stars, they are the rule. Current estimates, extrapolated from transit photometry data, suggest that perhaps 20% of Sun-like stars host an Earth-sized planet within the habitable zone, that orbital region where temperatures might allow for liquid water to persist on the surface. If our Milky Way galaxy harbors between 100 billion and 400 billion stars, even a conservative application of these probabilities suggests tens of billions of potentially habitable worlds exist within our immediate galactic neighborhood alone. Furthermore, the concept of habitability is itself expanding. We once considered only rocky planets orbiting G-type stars, but research now actively explores the potential for life around M-dwarf stars, which are far more numerous, or even subsurface oceans on icy moons like Europa or Enceladus, kept warm by tidal heating generated by massive parent planets like Jupiter or Saturn, a scenario suggesting that the necessary solvent for biology might not require a temperate stellar neighborhood at all. The core of the paradox, articulated by the physicist Enrico Fermi during a casual lunchtime conversation in 1950, remains startling in its simplicity. If the universe is so vast, so old, and apparently teeming with the requisite materials and opportunities for life to arise, where is everybody? Why, despite decades of increasingly sensitive searches, have we detected no unambiguous signals, no megastructures, no probes, no evidence of galactic colonization? This is the crux of the Fermi paradox, an argument that pits the high probability of extraterrestrial intelligence against the total absence of observational evidence. To systematically address this profound silence, the scientific community often invokes the Great Filter hypothesis. This concept, popularized by Robin Hanson, suggests that there exists at least one formidable, evolutionary bottleneck, a great filter, that prevents abiogenesis from consistently leading to advanced, interstellar traveling civilizations. The crucial, and terrifying, ambiguity lies in the filter's location. Is it behind us, or is it ahead of us? If the great filter lies in our past, it implies that one or more steps leading to human-level intelligence were extraordinarily improbable. Consider the journey from sterile primordial soup to self-replicating RNA or DNA. The transition from non-life to life, abiogenesis, remains one of the most significant unsolved problems in science. Despite advances in prebiotic chemistry, such as the Milieu experiment demonstrating the spontaneous formation of amino acids under early Earth conditions, the exact pathway to organized, metabolizing protocells is obscured by time. Perhaps the spontaneous assembly of a functional, self-replicating polymer capable of Darwinian evolution is a trillion-to-one event, a cosmic fluke that only occurred here. Another past filter could be the jump from simple prokaryotic life to complex eukaryotic cells, a transition that took nearly 2 billion years on Earth, involving the seemingly miraculous event of endosymbiosis, the incorporation of one bacterium by another to form mitochondria and, later, chloroplasts. Or perhaps the filter is the evolution of true multicellularity, or the development of large brains capable of abstract thought and technology, or even the specific sequence of events leading to sexual reproduction and genetic diversity. If any of these steps are the great filter, then we are rare, perhaps unique, and the galaxy is largely silent because the necessary prerequisites for intelligence are almost never met. However, the scenario where the great filter lies in our future is significantly more alarming. This alternative suggests that life, even intelligent life capable of radio astronomy and basic spaceflight, arises relatively frequently, but something invariably prevents these civilizations from achieving interstellar dominance or even long-term sustainability. What cosmic or self-inflicted calamity could be so universally effective? One major category of future filters relates to self-destruction, often termed as doomsday scenarios. The rapid development of destructive technology is a common theme. Nuclear warfare, though currently held in check by mutually assured destruction doctrines, remains a persistent threat. More insidious are the risks associated with uncontrolled artificial intelligence. The hypothetical singularity, where machine intelligence rapidly surpasses human comprehension and control, poses an existential threat if its final goals are misaligned with human survival. Nick Bostrom's work extensively details the instrumental convergence where, regardless of its ultimate goal, an advanced AI might find it instrumentally useful to acquire all available resources and eliminate potential threats, including its creators. Furthermore, runaway climate change, driven by industrial activity and the release of greenhouse gases like carbon dioxide, methane, and nitrous oxide, represents a planetary-scale self-inflicted wound. While Earth's climate system possesses inertia, the crossing of critical tipping points, such as the irreversible melting of major ice sheets or the thawing of vast Siberian permafrost releasing trapped methane, could render a planet permanently hostile to its dominant technological species, effectively setting a civilization back to a pre-industrial or even pre-biological state. The sheer energy requirements for sustained advanced technology might also necessitate resource extraction rates that inevitably lead to ecological collapse. Beyond self-destruction, astrophysical threats constitute another potential future filter. Gamma-ray bursts, incredibly energetic explosions associated with the collapse of massive stars into black holes or the merger of neutron stars, can sterilize vast swaths of a galaxy if directed toward a habitable planet. While the probability for any single star system is low, over galactic timescales, such events are frequent enough to act as galactic reset buttons, wiping out civilizations before they can spread widely. Similarly, nearby supernovae, though less energetic than GRBs, can strip away a planet's ozone layer, subjecting surface life to lethal ultraviolet radiation. The timeline for such an event occurring within a relatively close proximity, say within 50 light-years, is statistically non-trivial over millions of years. Even less dramatic but potentially civilization-ending phenomena, such as sustained asteroid or comet impacts, though mitigated by planetary defense mechanisms in advanced societies, might be more devastating to a nascent technological species lacking such infrastructure. The SETI, Search for Extraterrestrial Intelligence, effort, which has actively scanned the skies for radio signals for over 60 years, provides the observational backbone to this paradox. Projects like Project OSMA, the Modern Allen Telescope Array, and the Breakthrough Listen initiative employ massive radio telescopes to listen across a wide spectrum of frequencies, focusing particularly on the water hole, the quiet radio window between the emission lines of hydrogen and hydroxyl radicals, a band that hypothetical extraterrestrials might logically choose for communication. The null result thus far, often termed the Great Silence, is perhaps the most compelling piece of data we possess. If even a small fraction of the billions of habitable planets hosted a civilization equivalent to, say, the early 20th century on Earth, broadcasting detectable signals for just a century, the probability of detection should be significantly greater than zero, given the age and size of the galaxy. The Drake equation, developed by Frank Drake in 1961, attempts to formalize the estimation of the number of detectable intelligent civilizations in the Milky Way, represented by the variable $n$. The equation multiplies 7 factors, starting with the rate of star formation, the fraction of those stars with planets, the average number of habitable planets per system, and then proceeds through biological and sociological hurdles, the fraction of habitable planets where life actually arises, the fraction of life that evolves intelligence, the fraction of intelligent life that develops technology capable of signaling, and finally, the average longevity of such a communicating civilization. $L. The crucial takeaway from the Drake equation, despite the widely speculative nature of many of its variables, is that the final result $N is exquisitely sensitive to the last term, $L. If $L is very small, if civilizations tend to destroy themselves shortly after achieving radio technology, then $N plummets toward 1, suggesting we are alone or nearly alone within our observable horizon. If $L is vast, if civilizations persist for millions or billions of years, then $N skyrockets, and the paradox deepens profoundly. To escape the constraints of the paradox, some theories propose that advanced civilizations exist but employ communication or expansion strategies fundamentally undetectable by our current methods. This leads to the concept of non-obvious civilizations or alternative technological pathways. Perhaps truly advanced societies quickly transition away from wasteful, electromagnetic spectrum broadcasting, viewing it as an archaic, energy-inefficient mode of communication, akin to us using smoke signals. Instead, they might utilize quantum entanglement for instantaneous, localized communication, or employ tightly focused, neutrino-based signaling that our current SETI arrays are ill-equipped to intercept. Another class of explanations revolves around energy consumption and Kardashev scaling. Nikolai Kardashev's typology classifies civilizations based on their energy utilization. Type 1 utilizes all the energy reaching its home planet from its star. Type 2 harnesses the entire output of its star, perhaps via a Dyson swarm or sphere, and Type 3 controls the energy output of its entire galaxy. If life frequently reaches Type 1 or Type 2 status, we should see massive astroengineering projects, waste heat signatures, stellar dimming patterns, or gravitational distortions, which would be observable over interstellar distances. The search for these technosignatures is a rapidly growing field, focusing on anomalous infrared emissions, suggesting Dyson structures or non-natural atmospheric compositions. The perplexing dimming patterns observed in Tabby's star, KIC 8 for 62520, for instance, prompted intense speculation about megastructures, though later analysis increasingly favored complex, uneven circumstellar dust clouds as the most probable, if still unusual, explanation. The absence of widespread, unambiguous Dyson spheres remains a powerful constraint on the frequency of Type 2 civilizations. The Zoo hypothesis, a more anthropocentric explanation, suggests that extraterrestrial intelligence is aware of us but deliberately chooses non-interference, treating Earth as a protected nature preserve or a scientific subject under observation. This mirrors humanity's own policies regarding uncontacted tribes. To maintain such a quarantine across an entire galaxy, however, requires a near-perfect level of coordination and consensus among potentially millions of diverse civilizations, a logistical feat arguably more difficult than achieving interstellar travel itself. Furthermore, any single civilization breaking the pact would reveal the others, necessitating an enforcement mechanism that itself might be detectable. The planetarium hypothesis, a radical extension, posits that our entire perceived reality, including the night sky, is a sophisticated simulation created by a vastly superior intelligence, perhaps to study the evolution of life under controlled conditions, or simply for entertainment. If this were true, the paradox dissolves, as the creators simply choose not to populate the simulation with other visible civilizations. While untestable by definition, the mathematical argument suggesting that a post-human civilization would almost certainly possess the computational power to run such simulations lend this idea a disturbing, though speculative, scientific weight, related closely to Nick Bostrom's simulation argument. Returning to the tangible constraints of physics and engineering, the sheer scale of the galaxy presents an immense barrier to expansion, regardless of motivation. Interstellar travel, even at velocities approaching a significant fraction of the speed of light, requires monumental energy expenditure. To accelerate a single kilogram to 10% the speed of light requires kinetic energy equivalent to the annual energy consumption of a medium-sized industrialized nation. Current propulsion concepts, such as fusion rockets or antimatter drives, remain theoretical or technologically nascent. While relativistic travel offers a path to traversing the galaxy within the lifetime of a single civilization, the time required to colonize the entire Milky Way, even at slower, sub-relativistic speeds, is estimated by some models to be several million years, a timescale long enough to allow for multiple filter events to intervene. Consider the colonization time scales. Even if a civilization develops self-replicating von Neumann probes, hypothetical autonomous spacecraft capable of manufacturing copies of themselves from local raw materials, the colonization timeline is still dictated by the speed of light, $C. If the probes travel at 1% of $C, and the galactic disk is 100,000 light-years across, the minimum colonization time, assuming exponential replication, still spans hundreds of millions of years. Given that complex life on Earth has existed for only a fraction of a billion years, this suggests that if colonization is the norm, it should have already occurred, given the galaxy is billions of years older than Earth. The lack of Grey Goo-style expansion argues strongly against highly replicative, fast-moving probes being common. The astrobiological search continues to evolve, moving beyond traditional radio SETI to focus on biosignatures and technosignatures. The James Webb Space Telescope, with its unprecedented infrared capabilities, is now meticulously analyzing the atmospheres of exoplanets in the habitable zones of nearby stars. We search for atmospheric imbalances that defy known chemical equilibrium, such as the simultaneous presence of large quantities of oxygen and methane, which on Earth requires constant biological replenishment. If such a disequilibrium is found on a distant world, it would be a powerful indicator of life, even if that life is only microbial. Furthermore, the detection of specific industrial pollutants or artificial spectral absorption lines could serve as technosignatures. The study of extremophiles on Earth provides crucial insight into the resilience of life, potentially expanding the range of what we consider habitable. Organisms thriving near deep-sea hydrothermal vents, surviving pressures exceeding 1,000 atmospheres and temperatures approaching 150 degrees Celsius, or those living within nuclear reactor cores, demonstrate that life can exploit energy gradients far removed from temperate, surface sunlight. This bolsters the case for subsurface oceans on icy moons or even life within the atmospheres of gas giants, provided there is a persistent energy source and solvent. The search also considers the possibility of silent civilizations, those that have transitioned into a state where their existence is profoundly subtle. Perhaps the ultimate form of sustainability involves achieving perfect energy efficiency, minimizing waste heat and eliminating electromagnetic leakage. A truly mature civilization might exist in a state of near-perfect equilibrium with its environment, a state we would be entirely unable to distinguish from a lifeless, pristine world. They might harness vacuum energy or utilize computational matrices so dense and efficient that their footprint on the observable universe is effectively zero, a perfect camouflage dictated by the very laws of thermodynamics when applied to long-term survival. Furthermore, we must confront the limitations of our own biological and technological biases. Our search is overwhelmingly anthropocentric, predicated on carbon chemistry, liquid water, and electromagnetic communication. What if life is silicon-based, utilizing liquid ammonia or methane as a solvent? What if their sensory apparatus perceives reality across entirely different spectra, rendering our radio windows invisible to them, or vice versa? The very definition of intelligence is an entanglement of our own cognitive structure. We seek reflections of ourselves, potentially missing radically different forms of sentience that have evolved under alien selective pressures. The philosophical implications of the Fermi paradox are as potent as the scientific ones. If the filter is behind us, then humanity represents a fragile, precious rarity, an almost miraculous outcome of cosmic chance. This imbues our stewardship of Earth and our continued technological progress with an almost sacred responsibility, as we might be the only mechanism through which the universe can know itself. If the filter is ahead of us, the realization should serve as a profound, immediate warning. It implies that every civilization that has reached our current level of technological capability, the ability to manipulate fundamental forces and potentially destroy the biosphere, has inevitably failed to navigate the subsequent transition. Our current global challenges, climate instability, nuclear proliferation, and the nascent risks of uncontrolled advanced technology, are not merely political or social issues, they are the potential manifestations of the Great Filter itself, universal stress tests that almost no species survives. current astrophysical surveys continue to refine the constants within the Drake equation. The discovery that planets are ubiquitous means the early terms are high. The ongoing search for biosignatures via JWST suggests that the early biological hurdles might be relatively low, perhaps making abiogenesis common, thus pushing the most stringent filters further along the timeline toward complexity or longevity. If we find even simple microbial life on Mars, Europa, or Enceladus, the probability of life arising elsewhere increases dramatically, effectively ruling out the abiogenesis step as the primary great filter. The future trajectory of humanity's search will likely involve deeper, more targeted surveys. Next-generation telescopes will search for more subtle technosignatures, perhaps atmospheric ozone depletion patterns caused by industrial activity or complex, non-natural spectral absorption features that indicate large-scale manipulation of planetary environments. Furthermore, the potential development of interstellar probes, perhaps inspired by the breakthrough Starshot concept aimed at reaching Alpha Centauri within a generation using laser-pushed light sails, represents a reciprocal search strategy. If we can send out automated probes that explore and report back, we may one day find evidence of civilizations that failed to broadcast but whose artifacts or ruins remain detectable across the vastness of time. In conclusion, the absence of evidence is not evidence of absence, but in the case of the Fermi paradox, the silence is deafening enough to demand an explanation. Whether the answer lies in the sheer improbable improbability of life's initial spark, the catastrophic tendency of technological species to extinguish themselves, or in the realization that truly advanced intelligence operates in ways so foreign to our comprehension that we cannot perceive their presence, the resolution of this paradox will fundamentally redefine humanity's understanding of its significance. The universe remains vast, ancient, and patient, and for now, we remain alone in the spotlight of our own self-awareness, listening intently to the immense, echoing quiet. The next breakthrough in astrobiology, the next atmospheric analysis, or the next decade of radio scanning might, at any moment, collapse the statistical uncertainty and reveal whether we are the lucky survivors of a cosmic gauntlet, or merely the next contestants awaiting the inevitable final challenge.